And I'd like to now cover the third document. Andy very kindly spoke about ASTM and ASHRAE standards, but there is another document, which is ISO 16000, which is a series at the moment of 44 different documents covering a lot of issues on indoor air quality. And number 26 deals specifically with guidance on how to use CO2. So, sorry, there we go. Sorry, too much. So what we'll first of all look at ISO 16026. Also, we need to look at 16000-1, which gives some overall generic information. And we'll be looking at characteristics of the indoor environment, ventilation system, sampling duration and location, making parallel measurements and analysis. And depending on how time allows, I'd like to also see what we can talk about CO2 detection technologies, one of my favorite subjects when I was at AlphaSense, on NDIR technologies and the limitations on NDIR. Let's first look at the indoor environment characteristics. It is not static. There's human activity, the ventilation goes on and off, there's cleaning and cooking, air purifiers, there's emissions and sinks from surfaces, creating quite a dynamic environment. Also, the heating ventilation itself frequently causes stratification within the same space. And there's a big difference between outdoor and indoor air. In indoor air, we're often very close to the polluting sources, standing next to a kitchen, it's next to an oven or cooking source or something like that. That's quite different than the pollutants that we see in outdoor air. The air composition varies between the rooms, and it's less homogeneous than the outdoor air. And there are three components that I consider indoor air quality. There's first of all the oxidizing gases, that's chlorine, your bleach, ozone, NO2, and they will react with the VOCs, volatile organic compounds. There's also particles, ultrafines, fine, and coarse particles, with ultrafines becoming more important as we're appreciating from epidemiology and toxicology how they are dangerous. But their composition is not the same, and their particle size distribution is not the same than outdoor air. And people are frequently using outdoor air calibrated equipment to measure indoor air particle composition. That has its problems. And VOCs are a major concern because we're cleaning, cooking, we have pets, we have health products, and of course we have to rebuild our houses all the time. So there are a lot of reasons why the indoor air is quite different than the outdoor air. Let us start with the ventilation system. Do we need to measure in various locations in a space? Well, ISO says maybe not in very large spaces, an auditorium or large open plan offices. But we cannot assume homogeneity in complex spaces or where you have mechanical ventilation in small spaces. There can be dead zones and where you have very low air exchange rates. People have seen that you will have mold growing in certain corners of a room, but not in the rest of the room, as an example of poor homogeneity. And ventilation effectiveness is achieved when the concentrations in the extract air and the indoor air at the sampling point are identical. It's important when you're measuring CO2 that you have a baseline, and that is established when the indoor air and the extract air are consistent. And the homogeneity of the air distribution in a room can be investigated using CO2 concentrations, and you follow the extract air and the sampling point closely at different points in the room. So we're now seeing that you just don't go into the center of the room and stand there, take a measurement, and walk out. You haven't completed your job. You don't understand that room at that time. How long do you ventilate? Well, basically, your measurements start after the room. If you're going to do an ideal measurement, you'll wait till the room has been vigorously ventilated until the concentration is set in ambient air. That's your baseline. And then you proceed to have people come into the room or something. And this is an ideal situation, which you cannot achieve normally, as Mark was saying, that you just don't get that steady state that you'd like to have, and beyond your state as well. In mechanically ventilated rooms, you operate the VAC equipment for 1 hour before first taking the base measurement in an unoccupied den room, and then in the presence of users in the room, also if you have free ventilation as well as VAC controlled mechanical ventilation. So you take your baseline and then you introduce your sources of CO2, which are human beings normally. If you're very lucky and you have the time and the equipment to do it, then a tracer gas using SF6 or a high concentration of CO2 is a very good way of measuring the air change rate. Normally, we don't have that. We use human beings as our sources of CO2, and recording starts 15 to 30 minutes after injection of the additional CO2 into the room air. In this case, it can be no more than the fact that people have gone into the room and are occupying it. But if you don't know the number of people in there and whether they're leaving and coming in there, you have a variable source, then you have additional problems in your calculation. Interestingly, just a simple table fan encourages circulation in a small to medium volume space, a good way to encourage homogeneity and be a bit more comfortable. And if you are determining ventilation effectiveness, and I was going to put the equation up for that, but we're trying to be short on the time here. If you're to be determined by the steady state concentration in a mechanically ventilated occupied room, then it's measured at various points after about 2 hours after starting up the VAC plant. So it takes about 2 hours from the time that you have a baseline until you have something that you're hoping is steady state, if you're going to make a steady state measurement. It's quite a long time, but that's how long it takes spaces to stabilize. If the emission characteristics of a source are to be recorded, or if you don't know about the source of combustion gases, then the CO2 concentration is recorded over a longer period. So you've got a problem of space and you've got a problem of time. And to be honest, most of this kind of makes sense if you think that you have people generating CO2, and you can also possibly be looking for an emission source, such as an open fire. Any combustion source also generates CO2. Where do you measure it? How do you measure how many points? Well, the rule is if you take a room with a surface area of 50 square meters, and that's all your 6 surfaces in a box, then you locate a single point at about 1.5 meter height. That's our typical breathing height. And don't measure near the walls, at least 1 to 2 meters from the wall. And for larger rooms, there's more sampling sites that are needed to determine any concentration gradients. Again, this is sensible. The measuring device must be not near the sampling point, and people should be 1.5 to 2 meters from the sampling point. If you're too close to it, you are basically contaminating the source, because humans breathe out thousands of ppm of CO2 and will therefore give you spikes if you're breathing too close to your sensor. When you're searching for an unknown source of combustion gas, of combustion exhaust gases, then you take a measurement, keep moving it every 5 to 10 minutes. So there you have a stabilization time of about 5 to 10 minutes. You don't need to record all 5 or 10 minutes, but just a rule of thumb, 5 minutes to 10 minutes in a spot. It's best if you average over that period, but you can also take a spot reading. And there you're looking for the site of the highest concentration. So it'd be nice if you had an instrument that measured average and min-max. That would be useful. And when you're measuring in mechanically ventilated rooms, the point at which the supply air enters a room must be measured. That gives you the outdoor pollution concentration of the CO2. And also you should be doing your any other pollutant measurements, because the assumption that the ambient air is clean is a very weak assumption to make. Somebody measured, we commented on humidity earlier. Well, parallel measurements of the outdoor air and your metaparameters are very useful. Now, we keep, Biane reminded us that we need to measure indoor versus outdoor, and it's always the difference that matters, and so does Andy measure that, and I agree, it's a delta CO2 concentration, not the absolute. So you need, and if you're in rural, you can make assumptions of 425 ppm, which I believe is Hawaii's number this year, and next year it'll be 427. But you should always measure the outdoor air, because in cities, as we just saw in Copenhagen, that it goes can be much higher. Okay, don't get closer than 1 meter from the wall of an outdoor building, just because you have surface effects and boundary layers. And in measuring outdoor air, remember there can be vertical concentration gradients very easily. And if the building is equipped with an HVAC system, then the outdoor air should be sampled near the air intake. Again, very sensible. And I'm a great believer in wind direction, wind velocity, and other weather conditions are helping you when you look at data and you start to not understand why you get some unusual answers. Have a look at what was the wind direction and how windy was it when you took those measurements, because the outdoor air affects a lot more than you think. And it's always sensible to measure accurately temperature and humidity and the barometric pressure, which can be used to improve reading accuracy. Barometric pressure corrects the straightforward thermodynamics of measuring particles in a fixed volume, which is what we do with NDIR. Measurement uncertainties inevitably occur. They can be due to the limits of your measuring device or your procedure, and also in your sampling and your analysis. So there's lots of opportunities to create error, believe me. You must establish how to describe the measurement uncertainty. I had that discussion with somebody just a couple of days ago, and which performance characteristics are used when you describe the results of a measurement report. There is no generic method for calculating uncertainty. It depends on the equipment and the protocol and where you are measuring and what are the important interfering parameters you must consider. And when calculating uncertainty, you refer to the guide to the expression of uncertainty in measurement. We just call it GUM. GUM is our Bible. And so if you're talking uncertainty, talk GUM. So in summary, the built environment is dynamic and it's different from the outdoor air. You must characterize the ventilation effectiveness, and importantly, start by determining your baseline concentration. Wait for a couple of hours for steady state when you're measuring a steady state CO2 measurement. And when you're doing tracer decay, which I think is a better technique, then you need to sample regularly. Okay? You measure typically at 1.5 meter heights and 1 to 2 meters from walls, and keep away from the measuring point, please. Okay, and you monitor the outdoor air. It's outdoor minus indoor CO2 concentration. Also, temperature, humidity, pressure should be recorded, and wind speed, wind direction. And finally, calculating uncertainty is not simple. Refer to GUM. We have a few more minutes, and I'd just like to tell you a bit about measuring CO2 technologies. We have diffusive and pumped samplers, and there's basically, I'm going to go past that. They're relatively inexpensive for diffusive samplers, and they're commonly put around. But these days, NDIR is a lot cheaper. It's very affordable. It's now down to Amazon prices. But generally, NDIR comes in three prices and 3 quantities. I missed a zero there. It's 30 ppm is plus or minus 3% is $400 to $100 for a sensor. And if you want 50 ppm plus or minus 5% of the reading, you pay less, $150 to $50. And if you want something that goes up and down with numbers, then you can get it for under $100 and that's going to be plus or minus 200 ppm. So you get what you pay for. 2 reference methodologies are cavity ring down and TDLAS, tunable diode laser absorption spectroscopy. They're the gold standard, but they cost thousands of dollars rather than hundreds of dollars. NDIR is now the dominant technology for measuring CO2, and they perform well. And the price used to be $100 to $200. They're now $15 to $40 for the sensor only. You'll pay more for an instrument because that includes batteries, microprocessors, displays, cases, servicing, etc. So, but the sensors themselves sell for that price, and it follows the Beer-Lambert law, which you can look up if you wish. What is important is we now have bright near-infrared and mid-infrared LEDs are now available, and they offer new opportunities for stability and pricing and very low power. And on the detectors, they're mainly photodiodes, but companies like Sensirion offer photoacoustic, and Gasera, they offer photoacoustic methods where the detector is not a photodiode, but it's a microphone. And the pressure and the power requirement for NDIR, which used to use tungsten light bulbs, has dropped from 200 milliwatts down to less than 2 milliwatts as we move to pulsed LEDs and even lasers. And you can see here that NDIR can be used for a lot of different gases. Of course, the main one is the CO2 here in the blue there. That's the main. And whenever you worry about where is the water showing up, and we have what's known as the 3 to 5 window where water isn't available, isn't absorbing because water will so dominate your signal. But that CO2 sits in a very nice area of no water absorption, and there's not a lot else around it. And here's a typical what you get with a tracer gas, and this is from 8 different sensors, all working together. And you can see they're plus or minus 50 ppm at about 7 to 800 ppm of CO2. So you can get reliable, what's called repeatable, and I believe the word is precise, but not necessarily accurate sensors. And we're just about there. We have just 1 minute over just to show you there's a discussion about instability. And here we have some stable CO2 readings taken in different rooms in a house. And it's difficult to say it's plus or minus 50 to maybe 50 to 100 ppm just because they're not stable the time. It depends on the occupancy, the ventilation state, etc. And lastly, when you look at gas decay, that's what you want to see. You want to see a nice decay curve. That was done in Greentown Labs in Cambridge, Massachusetts. And you can analyze these kind of decay curves to get a good sense of the air change rate. So we now have LEDs, NDIRs dominating, and you can get anywhere at, if you pick 425, which is ambient air, you're going to be 60 ppm accurate, plus or minus 60. And at 1,000, you'd be 120 if you're buying a decent CO2 sensor. And you got to correct for barometric pressure. And I personally prefer tracer decay, and a few of the other speakers today agree on that one. And with that, thank you very much.